Hello dear friends, welcome to another video of the Never Do Through the GUI, what you can do through the CLI. I am Vangelis and today you are watching Web API benchmarking Python Flask prod setup with Rust actix-web. So in the last video we benchmarked the Python Flask framework, but we used the built-in development server, and this proved to be quite inefficient, and this was pinpointed to me by some Python users. And they are right, this is why I created this prod setup, which I will show you. But I want to say that I went for the built-in development server because for each tool that I test, I use what comes bundled with it in order to run it. So I'm using the built-in functionality, and I'm not creating a fully prod environment. But in this specific case, it seems that this was quite inefficient and quite wrong, and the only way to correctly to benchmark the Flask application is to create a prod setup. So this is what I did. So let me show you. First of all, this is the application. We have this route that we are concerned about, and we serve 1000 users. And this is the setup of the server, of Apache server. We don't care about any of this. What we care about is the threads I use. I use 8 threads, as you can see, which map to the 8 threads of the Rust application, which map to the physical cores of my CPUs. So yeah, we have a similar setup. We are serving the Flask application through Apache. Let me close this and let's go to the browser in order to see this. This is the Flask application and this is the Rust application. So if we come here and I say sudo systemctl stop apache 2, you will see that the site is not served anymore. And if we start this, the site is served. So prod setup, it is in my local machine, but both frameworks will be using the same resources, so we're good to go. And I will start benchmarking now. While I was preparing this video, I noticed that the behavior of the Flask API is not consistent through Apache. There are some cases where the run is immensely fast, and there are some cases where the run is quite slow. We will try to reproduce this with various runs, and I suppose the reason is that for some for the cases where the run is very fast, I believe that there is caching involved of Apache itself, and when the caches are called, we have let's say the slow run. As I said, I will try to reproduce it here and see how it goes. So let's start by benching the Flask API. This is our resources. So what we will be benching is 50,000 requests and 1000 concurrent requests. And I'm starting. And we have the benchmark is running. I will benchmark this run against the Rust API, and then we will run some more times this benchmark towards the Apache server in order for you to see that there are some runs which are extremely fast, but most of the time this is the behavior of the system. This is the time that it needs to perform the requests. So let's wait here. Hopefully it will be able to Yes, okay, we have a result. Let's compare first. Let's run the bench for the actix-web. So we have the same amount of requests, same concurrency, and let's start. We are done. We will compare now, and then I will run some more runs here for the Apache bench and try to reproduce the quick response. So let's start here. Users, concurrency, yes. Time taken for tests, here we are. 58 seconds, 3.9 seconds. Failed requests 251. Non to 100 responses, we have 49,850. That's very interesting. That is very interesting. Let me make a curl request. Curl .0.0.1 users. What are we doing wrong? Copy. No, we have our users. We are not doing anything wrong. I paused the video, and what I saw is that the problem is the URL that we provided. For some reason it does not work like this, but it needs to run it like this. So this is why the requests were failing. So we will run this benchmark instead to this URL, which is the same in essence, but for some reason it was failing with the other request, with the other URL, sorry. So let me rerun the bench like this. So we are currently benchmarking, and let's see the system monitor here. There are always some kind of surprise, but it doesn't matter. We all learn through these mistakes or through these quirks of the systems. As you can see, I don't see anywhere the Apache being overloaded for now, and the system, as you can see, load is this, but at least now we are hitting correctly the API, and I suppose we will have our correct results. And at the same time, it seems that what I said in the beginning about some quick runs was totally false, because all the requests were failing. So this is why we had a very quick response by Apache. But in this case, where the requests are not failing and we have response, you see this is the actual throughput of the system. Let's go to the browser just to make sure. If we ask this, as you can see, it needs some time to respond, which means that yeah, we are overloading the API with our test. And we have this one. Total of requests completed is this amount of requests. As you can see, we did not manage to make them all, so bear with me. I will lower this to 30,000. or to 20,000 to gain some time. So let's benchmark again with 20,000, and I will modify the number of requests for the 20,000 for the Rust 2. Sorry for the long video, but what I'm trying to do here is to create a useful benchmark. So we will modify on the fly our variables and our our test in order to have some kind of useful data. The good thing is that the memory usage is not okay, we have a result. So let's benchmark. Let's see first of all if we have failed requests, non 200 responses. We only have 10, which means that we are hitting correctly the API. Okay, so let's bench this one with the same amount, not this, sorry, Rust. So we are benching Rust with the same amount of requests, 20,000. Where is the number of requests? Okay, 20,000 and 1,000, correct. Let's hit this API. Okay, we're done. Let's compare. Users, concurrency level, time taken for tests, 60 seconds, 1.8 seconds. Complete requests 20,000, failed requests 12, 0, non 200 responses 10, we don't have any here, requests per second 331, requests per second 11,000 and 121. Time per request 3 seconds. Time per request 89 milliseconds. Transfer rate 33,000 kilobytes. Transfer rate 1 million, etc., etc. You can see the number. And let's come down here. Percentage of the requests served within a certain time, milliseconds. These are the numbers. As you can see, across the board, Rust is quicker. So in my mind, we still have a huge difference in throughput, even though we are using a prod setup currently through Apache with 8 threads, as you saw, exactly the same resources like the Rust API. So let's proceed to the WRK now test. Let's get the WRK. Let's clear this. Let me prepare system resources, enter, and let's check. So we are hitting it with 6 threads, 1,000 concurrent requests and 1 minute. We don't see anything Apache related here. And it's logical because, as you can see, the CPUs are not performing at their best. Let's wait for WRK to finish. Okay, we have a result, so let's come here and start hitting our Rust API. actix-web, 50% approximately, 120 memory usage. The CPUs are quite loaded, as you can see. "60 seconds here, 60 seconds there." Done. Let's see. Latency 255 milliseconds, 54 milliseconds, max 2 seconds, 133 milliseconds, requests per second 75, 3002K, max request 353, max requests 4014K, 4.14K, requests, total requests 26,000, total requests 1,081,000, 252 gigabytes read, 107 gigabytes read, requests per second 435, requests per second 80,000, transfer 42 megabytes, 1.71 gigabyte per second. Socket errors, we had 393 requests that timed out, and in general non 200 or 300 responses 89. Here we have everything was correct, had the correct response status, so no failed requests. Again, the results, as you can see, are quite, there's a quite big difference between the throughput of the two systems. Of course, I am repeating the initial test I did with the internal development server was worse, a lot worse than this, a lot more worse than this. So I created this prod environment, and hopefully this provides better insight into the throughput of the systems. I want to say sorry to the Python users for the initial setup. If they felt I owe an apology, so I am sorry about the initial setup, and thank you for the pinpointing of the problem. And in essence, this is the information of this video. And just out of curiosity, because I want to try out the alternatives to WRK, the video ends here, but whoever wants to continue with me, I will bench with an alternative of WRK, which is written in Rust, and I will use it now. If you don't want, you can close the video now, but for you that are interested, we will also use this tool in order to benchmark and see what this will provide, if we have any kind of difference. No, the behavior of the system is approximately the same as you can see. And I will prepare, I have the command for the Rust API too. Cool, let's benchmark these two. Let's run. Again, as you can see, the throughput of the system is similar to the WRK tool. Just of curiosity, as I said, we will check also the results, the final results, and see if there's any substantial difference to the WRK tool. The CPU usage is the same with WRK, so we are done. Let's compare. Latencies: average 735, average 58, mean 0.12 milliseconds, mean 2.28 milliseconds, max 93 milliseconds, max 59,000 milliseconds, so 59 seconds. Requests total 23,000, total 1 million. Requests per second 395, 16,700. Transfer total 2.22 gigabytes, 99 gigabytes. Transfer rate. As you can see, the the differences are again the order of difference is the same, and we have also the percentiles here. 1 to 37 milliseconds, 65 milliseconds, 69, and 78 for the 99.9 number of requests. So we also have 278 errors. We don't have no errors here. So this is the information. As you can see, we have approximate results with this tool too. The difference is huge. This is the outcome. So hopefully you will find this video and this benchmarking info useful for your future APIs. Thank you for watching and have a great day.